My name is Philip Koza. I'm a senior software engineer at IBM. I'm not a JVM developer. I'm just a guy who ended up being responsible for the memory usage of our application. Everything we're going to discuss here today has been implemented, and frankly, I can't imagine supporting our application without it. So here's what we're going to cover today. We're first going to go over where Java uses memory, some of the reasons you can end up using too much Java heap memory, how to estimate the memory usage of your objects during testing, then how to estimate the memory usage of your objects during runtime, how to track and control your memory usage at runtime, how to minimize the amount of memory you're using, how to efficiently manage your threads in the presence of uncaught exceptions, especially out-of-memory error, and then we'll have a summary at the end. All right, so there's many different forms of memory usage that the JVM has. The first is your OS and your C runtime. Now, obviously, your C runtime is only if you've got a JVM written in C, but most are, so typically there is a C runtime. Then you have your native heap. The native heap is for things like direct byte buffers and JNI calls. There's your method errors, this is where your class objects are stored. There's your JVM stack. And then there's your heap. And this is where all your instances of objects you allocate with the new operator are. And you can get an out-of-memory error for just about any of the memory usage that the JVM has, except for the OS and C runtime memory usage. But typically, if you get an out-of-memory error, it's because of your heap usage. And that's what this presentation is going to cover. We're only going to be covering how to monitor and control your heap memory usage. Some of the benefits here, you can get better performance and then higher availability of your app. So how do Java heap objects use memory? Well, the memory usage of a Java object is composed of a number of things. The first is there's a certain amount of overhead. A lot of people aren't even aware that this overhead exists, but it can range from 8 to 24 bytes depending on the JVM. It stores pointer reference to your class object, various flag fields, and things like that. There's memory for your primitive fields, reference fields, alignment bytes. Almost all the JVMs seem to want to allocate objects on boundaries of 8. So typically all your objects are rounded up to be a multiple of 8. And then arrays have some extra bytes for size. Okay, so that's how Java uses memory. So what are the typical reasons your app can use more than you expected it to? Well, the number one reason is you just don't understand how your objects are using memory. Another reason is just overuse of delegation. You just have too many objects, referencing objects, and so forth. Too many threads. In this context, we're talking about the Java heap usage of a thread. Almost all threads are using some amount of Java heap memory, and so even if your threads are only using a little amount, if you've got hundreds and hundreds of threads, you can run out of memory. And then another reason is not using collection classes properly. And this is basically, there's many different kinds of collections: list, heap map, heap table, and they all have different memory use characteristics. And it can be hard to know which is the right collection for you. There's a really good talk later this week on Wednesday from 8:30 to 9:30 by Chris Bailey. It's called From Java Code to Java Heap. He goes over in great detail the memory usage of each of the collection classes and how to pick the right one. So I highly recommend you attend that talk. So then there's memory leaks, and then just not cleaning up often enough. And then the final thing is finalizers. If you've got an object with a finalizer, it's not going to get garbage collected until the finalizers run. And the JVM doesn't guarantee when a finalizer will get run or if it's ever going to get run. So if you've got finalizers, you can end up having problems that are similar to a memory leak. You've dereferenced the object, but the memory is still being held. So what are the indications your app is using too much memory? Well, the first you're going to find is you're going to get degradation in your performance. This means both your responsiveness and your throughput are going to suffer. And allocating memory takes time, but it's fairly cheap compared to the cost of garbage collecting it. So if garbage collection costs are high, it's going to be because your garbage collector is just running more frequently because there's more memory. If you've got more memory, your garbage collector has to run more often. It has to sweep over and analyze all that memory. And when it gets to about 85, 90%, our testing has shown that your JVM really starts to thrash. It basically just gets to the point where it's getting harder and harder for it to find memory free, and eventually you get to the point where your JVM is spending all its time doing garbage collection. And then eventually that leads to out-of-memory error. So you really want to avoid this. Most JVMs, when you get an out-of-memory error, it's only going to kill the thread that actually got the error. It was just the one that was trying to get memory when there wasn't any more. It may be the one that was using a lot of memory. It may be that thread wasn't using hardly any memory at all, but it's just the poor sucker that happened to get the error. So when that happens, you can end up with other threads just hanging and behaving really strangely. I call these zombie threads. And your JVM might crash, but it might not happen right away. So, typically when you get out of memory error, it's just too late. So you really don't want to wait to start thinking about how to control your memory usage of your application until you get an out of memory error. So now I'd like to discuss the impact of performance on long-lived objects. In most JVMs, the default memory allocation garbage collection algorithm is generational. It's the default in Oracle Hotspot. It's the default in IBM J9 from build 2.6 and later. In general GC, your objects are initially allocated into a young generation. And then if they live long enough, they get promoted into a thing called the older tenure generation. And GC in the tenure generation is a lot more expensive. So if you can reduce the amount of data that you have that gets stuck in the tenure generation, you can really increase your performance quite a bit. So it's hard to say for sure what objects are going to become tenured, but likely candidates are things that are stored in static structures, passed between threads, or stored in collections. And by definition, an object that's long-lived is going to tie up memory for a longer time, and it's going to increase the odds of you getting a out-of-memory error. It's still possible that you can run out of memory if you don't have any long-lived objects, but it's unlikely. And in order for that to happen, you have to be allocating some very large objects or be allocating a large number of small objects in a short amount of time. So how can you minimize the amount of long-term memory you use? Well, the first thing to do is delay allocating your objects until you need them. Lazy allocation. Make sure you clean up your objects as soon as you're done with them, and sure you're not going to need them again. You could try converting them to a more memory efficient form if you're not going to be needing them for a while. Convert them to a byte array. And of course, you should always try to design your objects to be as memory efficient from the start as you can. So you're going to want to control your memory usage. But before you can do that, you have to be able to figure out, you have to determine how much your objects are using. So, memory usage of your objects is going to depend on a lot of things. First and foremost is who your JVM vendor is. And the next biggest thing is whether you're 32-bit or 64-bit. And if you're 64-bit, you have to determine if you're using compressed references or not. I don't know that much about what exactly a compressed reference is, but my understanding is it's basically the JVM picks an area of memory that has a fixed address, and then it converts your references into offsets from that base address. And it's enabled in Hotspot by default in version 6, version 23 and later, and Java 7. And in IBM, you have to explicitly enable it with this compressed references option. So there's two basic ways that you can estimate the memory usage of your objects. I'm sure there's other ways, but these are the two most widely used ways. The first is using the runtime package, total memory and free memory methods. And the second is using the instrumentation package that the JVM provides. So we're going to talk about each of those in turn. So the classic way to determine your memory usage, and this was the only way prior to Java 5, was to use the runtime memory methods. So basically what you do is you first see how much memory you're using before you start. Then you allocate a bunch of objects of the type that you want to measure the memory usage of, and then you compute the difference between your before memory usage and after, and that's how much memory you used. Sounds simple, right? Well, it is, but there's a few complications, gotchas here. Unfortunately, it can be inaccurate, and it's mainly because because of the garbage collector, right? In order for it to be accurate, you've got to make sure your garbage collector runs before you estimate your memory use. And you really can't force the garbage collector to run. Even if it runs, you might not free up all the memory. It might not collect all the memory that's being used at that time. So typically what you do is you call system.gc a bunch of times, and you hope that that's going to increase the odds that the garbage collector is going to get run. Now you can minimize some of the impacts of this by allocating a bunch of objects and taking the average of them and then declaring that that's the memory usage for this object. Another thing you have to keep in mind is this thing called escape analysis. This was added in Java 6. And what that is the JVM can look at your allocations if they're inside of a method, and if it sees that there's no references to that memory outside of that method, if the references to that object doesn't escape the method, it can decide to just stick them on the stack. And if that happens, then it's going to look like they're not using any memory at all when you're measuring the heap usage. So you want to make sure that doesn't happen. You may have to, during your testing, have a reference, make sure you have some phony references to the objects outside of the method. So here's a code sample of this. Just going to go over this briefly. Basically, you have a factory. You declare a factory interface, which is one method, make object. You declare a bunch of implementations of that are going to allocate objects of the type you want to measure. Here we can see we got object, integer, long, float, double, so forth. Then you've got your main method, where you basically just call a method that's going to allocate objects of that type and measure their memory usage. And here we can see the method that actually does the memory usage. You can see that it's calling this runGC method to run the garbage collector a bunch of times. Then we get the amount of memory we used. We allocate our objects. We get the after memory used. We allocated a bunch of objects, so we take the average of them and we round up. And that's our memory usage. Oh, and here's some of those utility methods that are being used. Here you can see runGC. We're running it 25 times in a loop and sleeping a little each time. I found that this does get the garbage collector to run pretty reliably, but every JVM is a little different. You may have to tweak this a bit. Okay. So then the other way is to use the instrumentation package. So to use this package, it was added in Java 5. You have to allocate a method called premain. And it's going to have this exact signature. It's got to have this exact signature, premain, string args, instrumentation. And what that instrumentation inst parameter is the JVM is going to pass an object that implements the instrumentation interface to this premain method. And then you can use that instrumentation interface method, get object size, to pass the object that you want to measure the memory usage of, and it'll estimate the memory usage of it. Okay, so there's further little details you have to deal with here when you're using this package. You have to make sure you have a manifest file with this exact line in it. And also, to run a program that's going to use the getObjectSize method, you have to specify this Java agent option on your command line. And one thing to keep in mind is that you can't get deep memory estimates with this. If you want deep estimates, you're going to have to use something called reflection. So here's an example of using the instrumentation package. We define an agent class that defines the premain method. Then we have our own getObjectSize method that invokes the instrumentation interface object, getObjectSize method. Then we jar it up, and then we can use our agent class to get memory estimates. Here we're doing it for an integer array. So I've got a little chart here that shows the usage of these techniques to estimate some common objects. Here's the chart. I'm not going to go over this too much. One interesting thing just to notice is that for 64-bit uncompressed references, the IBM JVM uses about 48 bytes more than the hotspot JVM. That's because the IBM JVM has a few extra flags in the overhead area. But if you use compressed references, both the IBM 64-bit JVM and the hotspot are almost exactly the same. Okay, so using one of these two techniques, you can estimate the memory usage of your objects during testing. So which is better? Well, the runtime methods are the simplest, right? Instrumentation does seem to be more accurate, so I would say it's preferred if you don't need a deep memory estimate. If you need a deep memory estimate, instrumentation and reflection is probably the ultimate solution, but it's more complicated and it's a lot slower. So now you need to translate this knowledge into methods that are going to efficiently estimate the memory usage of objects while your app is running. So your goal is to write a method that's going to estimate the memory usage of your objects for every class you're going to track the memory usage of, right? And any classes that are referenced are going to need a separate method. So since you're going to need a separate method for every object anyway, you don't really need to get deep memory estimates during your testing. And to make this perform really well, what you want to do is you want to have utility classes where you've pre-calculated all the memory usage of things like primitives and standard objects and so forth. And then they're just static finals, or you just invoke those and you get your memory estimates. So your methods, what do they need to monitor? Well, you need to have them estimate your object overhead. You got to take into account your alignment policy, size of a reference, size of primitives, size of primitive arrays, and then any basic objects you're using like string and integer and big decimal and so forth. And then for collections, you want to measure the size of an empty collection, and you want to make sure you determine the overhead for any entries that get added to the collection. And it's really important to always, if you can't get it exactly right, overestimate rather than underestimate. Because it's better to just use a little bit less than you otherwise could than to run out and get an out-of-memory error. And you can always refine your estimates to make them better using the techniques we've discussed. And most likely the JVM is using more memory than you thought it was anyway. So how do you calculate the memory usage of your application's objects? Well, one way to do it is to have an interface where you just have one method called getMemoryUsage, or you can call it anything you want. And it should return a long. And then every class that you're going to track the memory usage of, you're going to implement this interface. And then each implementation is going to estimate the memory usage of its primitives and object references and so forth. And as I said earlier, you can do that as a static final, so you don't have to keep doing it all the time. And one thing to keep in mind is that a null pointer reference uses the same amount of memory as a real pointer. If you have any non-null references, then you just follow the pointer and invoke the getMemoryUsage method for that class. And this includes arrays. Now you want to make sure that if your alignment policy is that things have to be on a multiple boundaries of 8, that you round up the final result. Recursive reference, you have to watch out for recursive references. If you got to remember whether you've already estimated this, if you come back around to the object again in the middle of your estimation, you got to remember that so you don't get stuck in an infinite loop. If you got any shared objects, something that's just used by all your objects, you should just count it once or not at all. It may just be insignificant probably. Flyweight objects such as intered strings, catch integers, and so forth. Unless you're sure that it's really going to be interred, or the JVM is going to treat it as a flyweight, it's probably best to just assume it's not. But if you're sure, like it's a frequently used file name, for example, something you know that you've used before, then go ahead, sure, treat it as a flyweight. So you're probably thinking this sounds like a lot of work. Well, it really isn't, and the benefit really can pay off. First of all, you're going to find that most of your custom objects, most of your application's objects quickly devolve down to primitives and in your standard objects like strings and so forth. And you don't need to do this for every class in your application, right? You're only going to do it for the ones that you're going to track the memory usage of. And as we talked about earlier, it's long-term memory that really is what's going to kill you in your garbage collection costs. So it's recommended, don't bother monitoring trying to estimate the memory usage of your short-term objects, just the ones that are going to live a long time. Okay? And you can always, check the accuracy of your estimates against using the techniques we discussed earlier to constantly keep improving them, getting better. But in the beginning, always make sure you overestimate rather than underestimate. And we found it's very quick, right? We've never had any performance problems using this methodology, but we've had a lot of performance problems with not doing it. Because all you're doing is you've got these static finals and stuff, you're just doing some additions. You've got a few method calls you have to make if you've got objects referencing objects, but it's really quite quick. So here's an example. So we've got a class called work unit. It implements the memory usage interface. It's got some static finals for our primitive usages and our overheads. We've got this class has a string reference. It's got a reference to another custom class called request. And then we have this mem usage field. What that mem usage field does is if we've already estimated the usage of this object once, we're not going to do it again. If we haven't already computed it, we factor in our fixed overhead. We get the memory usage of our string. We get the memory usage of this request object by calling its memory usage estimate method. And then we round it up and have our total. So here's, this is basically the same thing. This is just the request class that it was referencing, showing how it's doing its memory usage. It's almost exactly the same. And there's its get memory usage method. And then here's some of the utility class methods. Get string memory usage. You got to factor in, of course, the length of the object. And then we have a rounding method to round up to a multiple of 8. Okay, so that's how we calculate the memory usage of an object. And so now we can use that to track and control our memory usage at runtime. So it's recommended you just have one logical pool of memory where you're going to keep track of your memory usage. You want to avoid separate pools. Having separate pools gets complicated, and then you end up with situations where one pool's got a lot of memory left, it's not using it completely, and then other threads may want memory and then they can't get it because their pool's all full. So it's recommended just to have one large pool. Now you can control your memory. There's two kind of basic ways to control your memory usage. There's static and then dynamic control. We're going to talk about each of those. So controlling your memory usage statically means you reserve the memory up front, when the app starts or when the thread starts. You don't actually allocate the memory. You're just reserving it, right? You're making sure that it's reserved ahead of time so it doesn't get all taken by other threads. And then with dynamic tracking, you're going to have a total amount that you keep track of for all your threads. And then every time you allocate an object that implements this get memory usage interface that we talked about, you're going to increment this total amount used. And then when you don't need the object anymore, you decrement it. And as we said before, you're only going to track your long-term memory usage, so you don't have to do this for everything. And you don't need to actually pay for any memory dynamically if you've already paid for it statically. And then you want every thread to kind of maintain a local total that tracks its memory usage that it's just using, because that's going to be helpful when we see later what you do if there isn't enough memory. So this global total, it's just a globally accessible wall, and you got to synchronize all your increments and decrements of it, but you can buffer your increments and decks of it. That's what we do. We just buffer them up into 32K buffers and of the increments and decrements. It's not actually storing any memory in these things. Just you're actually delaying when you're going to increment the global total, and that really just cuts down on the synchronization cost. It's not really even an issue. Now, the absolute limit on your memory is, of course, what you specify with your XMX parameter when you started your JVM. And your dynamically tracked memory, well, it can't have all that. You can only let it have what's left over after you've accounted for everything else. So one example of everything else is your static reserve memory. So when should you allocate your memory statically? Well, some good rules of thumb are it's for things like your application just has to have it. You can't wait, have your app for this particular usage, go and ask for it and then be told that there's no memory left. So it should be something that there's not very many of. It should be something you're going to use a long time, and it should have some kind of static size or static upper limit. So what are some good examples of that? Well, some examples of that are like I/O buffers, right? Or a LIFO page cache. Those are all good examples of memory you could allocate statically. And you have to reserve a certain amount of memory for everything else your app's going to use that you're not going to be accounting for, right? So all your short-term objects that you're not tracking, just your basic overhead of having threads running and so forth. And you can do that as one lump sum, or you can have a per thread value, and then you multiply that by the number of threads you have, or both. We use both. So, and then one final thing is you want to reserve some memory to keep your JVM from thrashing. You don't want to go past about 85–90% of your memory utilization. So I recommend you reserve about 15% of your JVM max memory for just to keep your JVM from thrashing. All right, so the amount of memory you could have available for your dynamically tracked memory is your maximum memory minus all the other stuff you just reserved for your overhead and your statically allocated memory and so forth. And so every time you have a thread increment the global total, it just compares it against this limit, and if it's exceeded, the request is denied. So, okay, it's denied. What are you going to do, right? Well, if it gets denied, the simplest thing is the requesting thread has to handle it. So how can it handle it? Well, it could wait and try again. It could reduce some of its own existing memory usage. So it can throw away any objects that it doesn't need, any lower priority objects. It could write some of its data to disk. It could give up, throw an exception. Typically what we do is we basically have existing threads. When it asks for more memory, it goes and tries. Its first choice thing is to reduce some of its own memory usage. And that's why you want threads to keep track of their memory usage so that they can know how much memory they're actually using. And you could get a thread to try to get another thread to give up some of its memory. And that's possible, but it's more complicated, and we're not going to discuss that here. So now, if a thread decides to deal with its denied memory request by reducing its own memory usage, it doesn't actually need to resubmit the request again. You actually don't want it to do that, right? Because it just treats it as a swap of one of its memory usage for another of its memory usage. If it actually went and freed up that memory usage, decremented the total, asked for memory usage now again, it may not get it. Somebody else may have already grabbed it. So this way, you just have it swap out some of its existing memory usage. It's like a swap. It guarantees it gets the memory and not some other thread. Okay. So that's one way. Well, what are some other techniques? Well, soft references. That's built in. JVM provides it. Why not use soft references? Well, soft references have their uses. They can be really good for controlling memory usage of things that you can always get again, or you don't really need them, right? An example of that would be a web page image, right? If it gets reclaimed by the garbage collector, you just read it in from disk again, right? But soft references don't really work very well for objects where the only copy you've got of it is what's in memory. If it gets garbage collected, what are you going to do? It's gone, right? And you just have no control over when this is going to happen and what priority the JVM is going to decide. Which objects is it going to take, and you really want that level of control. So tracking and controlling memory usage is useful, but the best thing, of course, is to avoid allocating memory in the first place. So what are some ways you can do that? Well, you should always prefer arrays over complex structures. If you can use an array instead of a list, do it. It's much more memory efficient. When it comes to collections, avoid empty collections. You really want to have lazy allocation, not allocated collections. You're actually ready to stick something in there, right? You should size your collections appropriately, right? In some collections, if you just use the default size for it, like I think hash map's 100, and you're only going to stick 2 objects in there, you can end up using a lot of memory for no good reason. And choose the correct collection. There's many different memory, all the collections have different memory usage characteristics, so pick the right one. And again, there's that talk on Wednesday at 8:30 by Chris Bailey that goes over that in detail. And keep in mind that your class structure, how that impacts your memory usage, right? You want to avoid storing data in a separate class if all instances of that class need the data and it's not needed outside of that class. And conversely, you want to store info specific only to a subset of class instances in a derived class or in a separate class. So another thing you could do is you could convert your objects to something like a byte array, right? So if you know you're not going to need something for a long time, or if you're about to write it to a stream, if you're going to write something to a stream, you're going to be turn it into bytes anyway. Might as well just do that earlier and save on your memory usage. And then here's an example, one little technique you could use. Is if you stick a bunch of things in a hash map, and most of them aren't going to be used for a while, or maybe never used, right? You could convert it to a byte array, stick it in the hash map, and then when you go to get it, you convert it back. And you could have a little rule where you say, well, if once I fetch it once, that shows that it was needed by at least somebody, so I'll leave it converted in object form. And this can really cut down your memory usage if you've got these hash maps that have all these objects in them that are probably never going to get used. Of course, if you do this, you can't use generics because you're going to have a mixture of objects and byte arrays inside this hash map. And you should do cleanup as soon as you can, right? And one thing to keep in mind there is optimize for your mainline processing, not your exceptional processing, right? So, for example, if you've got some info you had to read from somewhere like a SQL database or something for a user request, right? Just delete it as soon as you send it back to the user, right? If for some reason it fails, and you just go get it again, right? And you don't have to keep it in memory sitting there just in case it fails. Now, of course, this is only a good idea if your failures are rare. If failures happen all the time, it's probably not a good idea. And of course, you can only do it if you have a way of getting that information again. And finally, use finally blocks as much as you can, right? You want to make sure that any memory you allocate gets freed. And if you're dynamically tracking it, right, it's being incorporated into this variable that you're tracking the memory usage of. You want to make sure that gets decremented if the thread dies. Because otherwise you can end up with what looks like a memory leak. Your dynamically your variable that tracks the limit is going to be saying there's this memory being used, but it's not really being used by anybody. And then, of course, there's object pooling, right? Object pooling can be a dirty word at times, but there are some limited cases where object pooling can be worthwhile, right? Object pooling doesn't actually reduce your memory usage, but it can reduce the cost to allocate and garbage collect it. So it's really only worth it for simple multi-purpose objects that are going to be able to be reused for lots of different things. So byte arrays are a great candidate for this because they can store any type of any object, and it's relatively easy to have a pool of them that you can then find something that's a close size to what you want to use. But the only good object pooling implementation I've ever seen that was worthwhile was one that dealt with page caches from a database, right? You've got these database pages, they're all 4K, they're all exactly the same size. It can really pay off with something like that where you're going to have everything's going to be exact same size, and you don't want to have to constantly keep allocating byte arrays all the time to store these pages. But so if you ever find your pooling is getting complicated, just stop. Leave complex memory management to JVM because it's going to do that better than you could for sure. All right, so now that we've got our memory usage under control, we're going to switch gears here a bit, and for the rest of this talk, we're going to talk about how to keep your threads under control. So, first thing you probably want to do with your threads is you're going to want to keep them balanced. And when I talk about balancing here, I'm going to talk about balancing their memory use, because that's what this talk is focused on, is memory use. So one way to do that is to feed the work to your threads via an array blocking queue, or your own synchronized buffering scheme. And you've got some size limit on this, right? And then if a thread's input queue gets empty or its output queue gets full, the thread has to wait. So keeps your threads from getting too far ahead of each other. And then the capacity of this queue or buffer is what's going to determine how far ahead your threads can get relative to each other. And to keep track to balance, to keep track of whether you've got the right proper of threads here, you can keep track, you have some statistics to keep track of the producers and consumers, and the number of times you have to wait to put or take. And if you have a lot of consumer waits, you need more producer threads. If you've got a lot of producer waits, you need more consumer threads. Now, there's an issue with the standard array blocking queue implementations. Now, the capacity of the queue is a number of objects, right? So unless all objects are sticking in there have exactly the same size, the memory usage of this queue can just vary widely. And you can run out of memory if you don't somehow limit or keep track of the memory usage of these queues. And that's actually happened to us. So what can you do about it? Well, one solution is to layer a logical queue over the top of your blocking queue. And this logical queue is going to be a buffered queue. So you're going to have lists, and you're going to store objects in these lists, and then what you're going to actually add to the queue are these lists, right? And the lists are going to be considered full when their estimated memory usage reaches a certain amount. So you're going to end up with a queue of lists, and they're each going to use the same amount of memory, okay? And then the maximum amount of memory you can stick in the queue is your buffer size that was actually declared for the queue times, or the buffer size times the queue capacity which was actually declared for the queue. So then the maximum amount of memory that this is going to use is going to be, you want to statically reserve it when the queue is created and then release it when the thread stops. This has, one of the nice things about using buffer queues is it has the additional benefit of you reduce the number of puts and gets in the underlying queue. Because even though it's not using classic synchronization, array blocking queues, the blocking queues, Java blocking queues do have a synchronization cost. And so this can help reduce that because you're not doing an actual put or get to the queue as often as you would if you're just sticking individual objects in there. Another advantage of it is it bases the amount of queued up work you have for any given thread by the amount of memory that work consumes. And it's probably true that larger requests take longer to process. So it's probably a better metric than just a number of requests. And now if you've got a buffered queue, one thing you got to keep in mind is that you got to make sure you flush the queue if it ever gets idle or has to wait. Because otherwise you can end up with things stuck and they're not getting out to the user or to their next destination. And so speaking of waiting, waiting indefinitely on anything is dangerous. So you want to try to never wait on anything forever, right? Because if you do, and there's another thread needs you to do something, like stop, for example, right? You're going to be waiting forever. And so you really want to use loops and timeouts whenever you can. That way you can wake up, see if anybody wants you to stop, or maybe there's a more urgent priority request to deal with. And if not, then you can just go back to waiting again. But I can't recommend this enough. It's really important you never wait on anything forever. All right, so despite everything you do, you get an out-of-memory error. All right? So why would that happen? Well, maybe your memory usage estimates were too low. Maybe all that memory you decide you weren't going to track used more memory than you thought it was going to. Or maybe there was just some short-term burst that overwhelmed the garbage collector and it just couldn't handle it. Or maybe you got a memory leak. Or there's too many threads. There's just a lot of reasons why this could happen. So if an out-of-memory error occurs, you're probably going to need a heap dump to see where, what was using the memory. So the IBM J9 JVM enables them by default. You can disable it, of course, if you don't want that. The Oracle hotspot does have them disabled by default. So if you want heap dumps with using hotspot, you got to enable it. And I highly recommend that you do this. You're only going to get a dump if you get an out-of-memory error. You're not going to get a dump for any little thing that goes wrong. You'll only get it for out-of-memory error, and it's really useful. But of course, if in the field in production you're getting lots of out-of-memory errors and it's overwhelming the customers' servers, you can turn it off. So when an out-of-memory error occurs, as I mentioned earlier, it's only guaranteed to stop the thread that triggered it. So you can end up with what I call zombie threads, right? The threads that were dependent on that thread that died can hang. The depth of the thread that got the out-of-memory exception, it might be enough to free up enough memory to allow things to proceed, but maybe not, probably not. So if this happens, you need some way of bringing down all your related threads. So one way to do that is with stock request objects. So, we'll talk about that in just a moment. But if you've got what I call a critical thread, it's a thread that your application just has to have. If this thread goes down, you're not going to get anything done. So if that happens, you probably want to bring the entire JVM down. We'll talk a bit about how to do that. Now, if you're having lots of problems with zombie threads, just everything, when you get out of memory errors, everything just doesn't seem to work. You might just want to bring down the entire JVM all the time, but you shouldn't have to do that. All right, so stopping with stop request objects. So what does that mean? Well, it means just have an object called stop request object that's going to indicate the thread should stop. And you'll have all your classes regularly check this thing, right? And of course, always before waiting on anything, okay? And it can work. It works the same whether the class is running as a thread or not, which is one of the nice things about it. You can actually also have different types of stop requests. Maybe you want the thread to stop right now. I don't care what you're doing, just stop. Or maybe you want it to stop gracefully. You want to tell the thread, finish what you're doing first, then stop. So you could have just one single stop request object for all the related threads, but that only allows them all to be stopped at once. So probably what you want is a stop request object that's got for the group of threads that are related, and then an individual stop request objects for each thread, so you can stop them individually. Now, setting it, you're going to have to be synchronized to set it, but stopping doesn't happen that often. And once you do it, it's stopped. And then reading it, of course, is going to happen frequently. But that doesn't need to be synchronized because it's not critical that you see the stop request right away. The JVM synchronization isn't going to guarantee that anyway. And it should be a Boolean enum. It should be atomic. So you shouldn't have any issues with the non-atomic updates. So that's how you can get your threads to stop. So how do you know when they've actually stopped? Well, you could use thread.isAlive, right? But to do that, you have to have a handle to the thread. And it presumes that the class is running as a thread. What if it isn't running as a thread? Maybe sometimes you run as a thread, sometimes you don't, right? So this doesn't really work for higher abstractions. So what can you do? Well, so it's better to just make that abstract. And one way to do that is to separate your runnable class from the class that's going to do the real work. Have your runnable class invoke the work class. Then your runnable class has a flag called isRunning, or whatever you want to call it, that keeps track of the run status. And then you have all your threads use this common runnable class. Another advantage of this, by having a common runnable class, is you can guarantee you have a common mechanism for handling uncaught exceptions, which we're just about to talk about. So using this technique, if you have a graceful stop, if the stop request was graceful, then you want your threads to wait for all the producer threads to stop before they stop. So that allows any in-flight data to get processed. And then if you have an uncaught exception or some other unexpected thread termination, you just can set the stop request to bring down all the related threads. So, finally, you gotta when you stop, you have to return control to the user. You want to make sure you don't return control to your user until you're sure that all the threads have stopped. Because if they decide they want to resubmit the request again, have it start up again, really weird things can happen if you try to bring up a new set of threads when the old threads are still running. So what can you do? How can you do that? Well, you could call thread.join and wait for the threads to actually physically stop. But to do that, you have to have a handle on all the threads. And while that's happening, you can't be responsive to any other requests. So it's probably better to just have your controller query your isRunning flag and wait for them all to be stopped. So here's an example. I'm not going to go into detail on this. It's just here for a reference. All right. Final thing we're going to talk about today is uncaught exception handling. So it's really important you have proper handling for your uncaught exceptions. They're the leading cause of unexpected thread termination. And if you've got any threads that are dependent on your threads, and if one goes down, you're going to have hanging threads. And hanging threads can be really hard to detect, right? Are they hung, or are they just in between bursts of traffic? You can have if you have proper statistics to monitor that can help you detect it. But it can take a while before you're sure that these threads are really hung. And then if you've got some kind of auto abort policy on hung threads, it's inevitable that you're going to end up auto aborting them too soon. So what typically ends up happening if you have hung threads is it requires a human to come in there and do something about it. And as we all know, that's bad. So by default, if you don't do anything, your uncaught exceptions are handled by the default uncaught exception handler. And all that does is write a stack trace to standard error. So that's rarely what you want, right? The stack trace may get lost, and if you did have your classes tracking your run status, it's going to be wrong. It's going to still say it's running because you never had a chance to set it to not running. And then what if you have any other threads that are dependent on that thread? You really just can't do anything. So don't let the default happen to you. So you want to make sure you have handling for all your uncaught exception handlers. And with uncaught exception handlers, you want to make sure you just do what you have to do. Keep it to the simple. Just do exactly what you have to do and no more. Because if you've got really complex uncaught exception handling, it could trigger other uncaught exceptions, and it gets really hard to debug because most likely what you're interested in was the original uncaught exception. If you get an uncaught exception, your uncaught exception handler, that's what you're going to end up seeing. The original one's going to get masked in most cases. And it's also probably true that your uncaught exception handler doesn't get tested, it probably hasn't been tested as much as your other classes. So you don't want a complex uncaught exception handler. All handlers at a minimum should log the error and stack trace to somewhere where you're going to actually be able to find it, like a trace file or something, and you should let the user know that this occurred. If you've got a run status, you should set that to stopped, error or some other equivalent, and to do that though you got to have access to the thread class state. So ideally the handler should also delete any dependent threads. You could have your handler alert the controller, which could restart that thread, but that's not recommended because any related threads, you don't know what state they're in. So the best thing to do, the safest thing, is just bring down all the related threads. And to do that, you don't actually have to have a controller, or if you do have one, you don't have to get involved. If you've got the stop request object, you just, when an uncaught exception happens, the uncaught exception handler sets it to stop, an abort stop, and then the threads, all of the related threads go down, and you don't have any hanging. So where to handle? There's three primary places. You can have a custom uncaught exception handler, you could catch throwable in the run method, or you could have a finally block in your run method. And we're going to talk about each of those in turn. So if you got a custom uncaught exception handler, there's three different kinds. You can have one per JVM, you can have one per thread group, and you can have one per runnable class. Per JVM, we mentioned this earlier, about all you can do is log the error and alert the user. That's about all you can do, because you don't have access to any of your specific thread classes or thread group state. If you do this, you set it via the static thread method, set up default uncaught exception handler. Another way is to have a custom uncaught exception handler per thread group. So this can guarantee you've got standard handling for a whole group of threads. This is a good choice for a default uncaught exception handler. You have your custom thread group class extend the thread group and override the uncaught exception method. Now this allows you to have some common code for your related threads, but you still don't have access to the individual runnable classes for your threads. So you could have code here to set the stop. You could register the stop object for those related threads with your thread group, and then have it set that. And then you set it true if an uncaught exception handler, uncaught exception occurs. And then you can have a uncaught exception handler per thread class. So this gives you complete access to the state of your class. You can log anything you want about it. You have all the information there. And it's guaranteed to be invoked. And to use this one, you don't use the static version of the set uncaught exception handler, you use the non-static version. And then you could catch throwable in the run method. Well, this isn't recommended in most cases. If you're going to do this, you want to make sure you do it at the highest level possible. Because you do it down inside any loops, you catch, let's say you catch out-of-memory error. Out-of-memory error occurs, you catch it, and you're still inside some loop. The thread isn't going to die, but it's not really going to be able to do anything. The JVM you're just going to be, it's going to be a zombie. You're going to have a zombie thread, and you just don't want that. There is only really one good reason to do this that I can think of, and that is that it can be useful if you've got a finally block that's got some complex processing in it, and you want to, if an uncaught exception occurs, you want to remember what the original one was. So in case an uncaught exception occurs in your finally block, you'll know what the original exception was. So you could catch throwable, log the original error there, then rethrow it, or do all your other handling there. So that way, if one occurs in the uncaught exception handling for the finally block, you'll at least know what the original exception was. But this is probably not worth it unless you're having this happen to you a lot. That goes back to what I said earlier. Keep your finally blocks and uncaught exception handling to a minimum. So then another way is to have a finally block in your run method. And if you're going to use this technique, what you do is you have some kind of flag, a handled flag, that you set to true at the end of every try block, every catch block. So if you ever get to the finally block and handled is false, you had an uncaught exception. So one of the advantages of this is that you have handling that's customized just for that class. You have complete access to its run state and everything. Disadvantages are every catch block has to set this handle flag to false, or it's going to be set to true, or it's going to be treated as an uncaught exception. And then finally, you still need an uncaught exception handler that's going to log the exception because the finally block doesn't have access to the exception. And one final thing to talk about is critical threads. So these are threads that your application has to have. And so if they stop, we mentioned this before, your application is not going to function. So you probably want to bring the entire JVM down. And the way to do that is to call system.exit. And one way to make sure this happens is to have a separate thread group for your critical threads. And that uncaught exception handler for that thread group, it calls system.exit. And your thread group uncaught exception handler for non-critical threads, it doesn't call system.exit. And that way your critical threads will bring down the JVM, but your non-critical threads won't. All right, so here's an example of using finally block. Not going to go into this in detail. Look, we're a little over. And so, in summary, we've seen that excessive memory use, using too much memory, can really have a bad effect on your performance. If you can estimate the memory usage of your objects, it's the first step to being able to control your memory usage. And then tracking and controlling it at runtime can really pay off to avoid out-of-memory error. There's a lot of ways you can reduce your memory usage up front. You can limit your threads, input queue and output queue size, so you can balance the memory usage of your threads. And then having a good framework for stopping, starting, and handling uncaught exceptions is really critical if you want to properly avoid hanging and other unpleasant behavior when out-of-memory error occurs. Okay, and that's it. Thank you. And I'll take questions now.